Well, thank you all for coming, and thank you very much for inviting me. Yeah, so my name is Memming Park, and today I'd like to tell you a little bit about my secondary interests, our exploration in the theoretical work of working memory and continuous attractor. This work has been spearheaded by brilliant current and former trainees, Abel Shagudi, who is a current PhD student, Piotr Sokol, who is a former student, now in the job market looking for a postdoc position, and Guillermo Martin Sanchez, who was a rotation student in my lab, now working with Christian Machens. Yeah, as announced, the title of my talk is Continuous Attractors, back to the continuous attractor, persistence of working memory computation without continuous attractors. So let's get started. So in science, dynamical system theory is the standard language. Zoom is not helping me. Interesting. This was supposed to be a video here. Let me just quickly check what is going wrong. Hold on a second. If this is not working, maybe all my videos are not working, so I should make sure that this works. Sorry about this. Okay, video is working now. Sorry about the interruption. So yeah, the dynamical system theories, as you all know, is the standard language for describing lawful changes over time, right? Any change in physics, fluid dynamics, mechanics, control, everywhere. And the standard way of writing it, and there are several ways of writing it, but of course, we can always write it as a differential equation like this, where your x here is the system state. F is your deterministic part of your dynamics that predicts, well, what's going to happen. And we may or may not have inputs or noise in the system. And of course, in recent years, people have tried to automate this discovery of underlying dynamical system from data. And of course, we have tried to do this in neuroscience as well. So in theoretical and computational neuroscience, the language of dynamical system has also become the de facto language for rigorously describing neural computations, all sorts of computations. For example, here I have a simulated spiking neural network that implements certain computation, and it can be understood if we distill this down into a two-dimensional phase portrait, where each of these axes correspond to the activity of some subpopulation. And this is where the black dots here are the stable fixed points. So you can see that the flow of the system converges to one of these two black dots, corresponding to one of the two subpopulation winning. So this is the winner-take-all computation that can be extracted from the phase portrait itself. So there has been many such examples of going from these networks to phase portraits, but also designing recurrent neural networks and recurrent systems from the simplified dynamical systems first. So you design the dynamical system first, and you try to find certain implementation. My primary interest, which I'm not going to talk about too much today, is the opposite. I'm trying to use statistical inference to recover these underlying dynamical systems from just observations. So when you have observations of spike trains of a population, some neural recordings over time, can we use machine learning tools like latent variable models or variational autoencoders or nonlinear state space models to extract these dynamical systems picture of what is happening? And these methods are necessary to battle many different features of neural data, including the fact that we get to have only a very partial observation, right? We're only sampling certain neurons out of the full population. We don't have the right temporal resolution sometimes, and it's very noisy. But that's another talk. Today, I'm going to tell you what I'm disturbed by in this recovery of this problem. Because when you're inferring these dynamical systems from data, if you change your data a little bit, you change your optimization algorithm a little bit, you get a slightly different picture, right? So all of these different pictures may cause an issue in terms of its interpretation. So I have started to develop some theoretical understanding related to this issue. So today I'm going to try to answer two theoretical questions. I'm not going to show you a lot of data today. The first question is, which dynamical systems can implement working memory? I'll define working memory for us. And for this question, I'll show you how this is tightly linked to a problem of learning as well. And also, I will try to link this to, the problem of continuous attractors or not, or a recurrent neural network without continuous attractor that does a similar thing. The second question I'll try to answer is the question of, when you have these kind of memory systems, how robust are these systems under, perturbations, let's say synaptic perturbations? The mathematical theory says it's not so robust, but maybe it's not a problem, maybe it's a problem. So if these intricate networks break down, do they break down in a certain way? Can we analyze this breaking down of these kind of memory systems? So to define memory, I mean, memory in general just means you have some past events that are that impact the system, and then later in time in the future, you can access whatever is in the system. And in particular in biological systems, there are many, many different possible memory mechanisms that that apply at multiple timescales, and well, including like long-term memory and so on. But I want to focus more on the short time scale version. So operationally, usually when you say working memory, it's defined for like a short time scale cognitive function. But in this particular talk, I want to focus not on its cognitiveness of the function, but more of its implementation. So what I call working memory is a mechanistic definition of working memory where information is stored in the reverberation of the recurrent network state. So that activity that's evolving over time is encoding the information, not the long-term synaptic changes or things like this. And in particular, I want not this memory content to be analog, which means continuous valued information, such as location, orientation, direction, intensity, distance, and so on. There are many behaviors that uses this kind of analog working memory, seemingly. For example, internal compass system, the head direction system, where the animals needs to keep, headings even when there's no sensory information. Navigation problem is a classic when you have to do path integration, also without, landmarks. Posture control, similar problem. And sensory evidence integration and perception problem, and so on. There are many, many problems that has not necessarily a pure working memory, but requires a working memory component to be able to perform a task over time. And of course, if you look at neural activity in particular brain areas, you find neural correlates of these working memory. So on the left, I was cut up a little bit. This is Christian Machens. in monkey prefrontal cortex, if you have this stimulus given to the monkey at a certain time point, this was a vibration on the finger, the firing rate of this neuron, this particular neuron, encodes that information as different levels of firing rate. And during the memory period or the delay period, this elevated firing rate is maintained over time. So there's this persistent activity that corresponds to, it seems to reflect the function of working memory. In the middle panel here is the famous central complex in Drosophila, where you have this donut-shaped structure, the ellipsoid body. And if you do calcium imaging on the ellipsoid body, you find a bump of activity that moves around as the fly rotates in darkness. So it's integrating its own angular velocity movement information and changing the location of the bump. So that location of the bump is seemingly representing working memory. And of course, in the entorhinal cortex, in rodents, you find grid cells where they are related to path integration and moving in 2D spaces. And these are very strange and very surprising because the default dynamics of a single neuron is really fading memory. They're not compatible with a persistent activity over time. And rather the typical time constants of synapses or the membranes are in tens or hundreds of milliseconds at most. In other words, these single neurons just typically forget what happened in a fraction of a second or so. But of course, if you have sufficient network activity, right, if you have coupling between the networks, this time constant can be lengthened. But if there's still a globally stable dynamics, these computations are mostly referred to as like fading memory systems or reservoir computing systems that have been successfully used in engineering. Instead of training recurrent neural networks, you can just randomly connect these networks to perform temporal tasks. But eventually they will all forget. So theoretically, the memory in these systems cannot last indefinitely. So let me introduce you to systems with stronger recurrent connections. Of course, these are also very well known. And once you have very strong recurrent connections, you can generate, multiple attractor states. So here I'm just showing you an example of a energy landscape of a dynamical system. So I'm just limiting myself to dynamical systems where you're following a gradient of an energy landscape. So wherever you have stationary points in the energy landscapes, you will have fixed points. And your neural state will fall into local minima, which would be stable fixed points. So this corresponds to the previous winner-take-all system where you had one of the two states that the system converges to. There's a continuous line attractor version of the system where this is exactly flat in the middle. So input from the system, from the external world for perceptual decision-making, for example, will push this internal state around, but it'll stay exactly where you put it, right? So you would have a continuum of stable states. The problem of these systems, one of the problems could be that it's not so resistant to a small amount of noise. So there's also this way of implementing similar computation with lots of local minima here. So a sequence of stable states. So small inputs will not move this state around, but big enough input, strong enough evidence will be accumulated and move the states around to achieve the computation. So this would be a sort of discrete kind of memory that's approximating this continuous kind of memory here. And this continuous line attractor object here is of the main interest for today. So because we're going to talk about its mathematical properties, I'll do just slightly more rigorous, not super rigorous here. Oops. A continuous attractor has a attractive manifold. For example, in this ring attractor on the right-hand side here, the blue ring is a ring manifold. A manifold is just like a plane or a line or a ring. And it's an attractive manifold, meaning if the states around it, there's a certain Bayesian of attraction where your initial conditions around the attractor, then it'll converge to the manifold. And on the manifold, there's no flow, meaning it's a continuum of fixed points. So anywhere on the manifold, you will not move forever, ideally, right? Because there's zero flow on the manifold. So this means a continuous attractor can be used to represent this continuous valued information. Let's say it's a orientation, which is a circular variable. It'll be conveniently can be translated to representation on a ring. All right. This has, again, nothing's new here. This has been implemented in many different ways. For example, the standard model for head direction cells have this particular form where if you record from the head direction cells, you will find that certain cells will have a certain tuning, right? Whenever the animal is heading certain direction, they will fire more and so on. So the question is, how do you implement such a system with recurrent dynamics? So one way to do it is to put a connectivity on the neurons such that when you arrange the neurons on a ring, you'll have self-excitation, or it could be inhibition dominated, that creates a bump that will generate a sustained activity of a bump. And in the limit of infinite number of neurons on the ring, these models will have infinite number of stable fixed points, and it will eventually become a continuous attractor. In recent years, I mean, this has been studied in so many different ways, so I will not go into too much detail. But in recent years, there was also an interesting variant of this system where you don't have to take the limit to infinity. This one was proposed by Neumann, where you have just 6 neurons. It's a linear rectified unit, linear threshold units that can generate a continuously varying ring attractor structure. So this is the firing rate profile of 6 neurons here, and with some input, the bump is moving along, and there's no approximation. It's precisely a ring attractor, a continuous attractor. Okay, so that was the introduction to continuous attractors. Now I'm going to make a strange jump here, and I'm going to talk about learning a little bit. So I claim that sustained propagation of learning signal, whatever the learning signal means, I will define, is sufficient for the existence of analog working memory. It can provide evidence for this. And I promise you that this detour in learning signals will come back to working memory very soon. But I'm going to talk a little bit about training recurrent networks to perform certain tasks that require temporal relations. And what I want to show you is that the analog working memory problem is related to this machine learning problem known as the exploding and vanishing gradient problem. So consider problems like this. You have some stimulus coming in, you have biological brain or a recurrent neural network, doesn't matter too much, and then later you have to produce a behavior. And time between the stimulus and behavior is quite long. There are many different tasks. Some of these are animal tasks that are more cognitive. Some of these are computer sciencey tasks that are designed to test how well you can train recurrent neural networks in a very difficult temporal learning task. But in these kind of tasks, you can make the delay between the stimulus and behavior quite far away. It could be in discrete time steps, thousands of time steps. And it becomes very difficult to learn because in theory, what needs to happen is whatever this relevant stimulus is for producing the right behavior has to be encoded as pattern of activity in the population. And that evolution of population activity somehow has to have some trace of this to be used later. So if your dynamical system is a terrible memory system, then it's going to be difficult to also learn the relationship through gradient descent, for example. Yeah, so the question is, there are many different kinds of dynamical systems you can have. Which of these dynamical systems can support this arbitrary long temporal relation learning problem? It may sound a little non-realistic, but it'll get back because it's easier to analyze this asymptotic cases. Just to set the stage, we're considering some recurrent neural network. Again, it could be biological or artificial. It has some adjustable knobs. These are synaptic weights. We have some loss function that we want to optimize for. This is the goal of learning. And I'm going to describe everything in terms of gradient descent or stochastic gradient descent, meaning that we will look at the partial derivative of the loss function at the current values of the weights, and then go downhill. And it can be argued that most of learning, if it's gradual learning, if you're learning a little bit of time to try to optimize something, is approximately a gradient descent or a noisy version of a gradient descent or an approximation version of a gradient descent, which is great. I mean, this is what everybody uses. This is what powers machine learning. But there's a limitation in terms of gradient-based learning. And this limitation is that mathematically speaking, this as long as your loss function is differentiable and your network is differentiable, you can do gradient descent to learn. But if there's noise, small gradients will be buried in noise. If it's a biological system with saturation, large gradients will be difficult to treat. And if you're using finite precision numerical floating points, again, you have a certain dynamic range that you'll be effective in. So if your gradients are too small or too big in magnitude, gradient descent is not practical and it often fails. And this is like a main failure mode of training recurrent neural network. And this indeed happens a lot in practice. And this is called the so-called exploding and vanishing gradient problem, or EVGP. And this EVGP is just everywhere. So we need to solve this EVGP. There are many heuristics in machine learning. I will not talk about details here, but basically like the ReLU, the LSTMs, all of ResNet, all of these techniques were developed because we had to deal with this gradient propagation problem. Why does this matter to us when we're talking about recurrent dynamics and memory? It's because the two questions are very similar. So what I call the memory question, where you have a recurrent dynamics of time t0 to time t, the memory question is, what does time x of t, this neural population state at time t, say about the initial condition x t0? And the sensitivity question, which is necessary for learning, asks, gradient descent-based learning, asks, how will xt change if I change the initial condition? What is the relationship? So one of them, the memory question, asks you the difference between if I change the initial condition by delta, these are two different memories at time t0. How does the difference evolve over time? And the sensitivity question is just the limit case of this, just the infinitesimal version of this, where you're looking at if I take a look at the derivative of the later state xt respect to the initial condition xt naught, this is just the limit of that memory question. And this sensitivity is what matters, what carries over all the gradient information, all the information needed to minimize the loss function or the error function. So for example, if you roll out the partial derivative of a loss function in a recurrent neural network, in the middle of this, you'll see this, the only term that in this product form, in the chain rule, the only term that matters over time is this, the sensitivity, x of t, x at t1 versus x at t. It could be different dimensions. And this basically is what backpropagation through time utilizes to compute things. And if this term goes to 0, you have vanishing gradient problem. So let me describe a case where what I just said may not be exactly true. So I have two systems. On the left-hand side, I have a system, a fading memory system. You have two initial conditions, x of t0 and x of t0 plus delta x. They both converge to a global stable fixed point here. As time goes to infinity, everything is forgotten. There's no sensitivity. Sensitivity will tend to vanish exponentially, probably. And memory will tend to go, it will be lost because it's going to be, the difference between the two trajectories will be smaller and smaller and smaller. So in this case, the two to go together. But on the right-hand side, we have this two stable fixed points, and there's some separatrix that divides the two sides of the dynamics. If you start from the left-hand side, you converge to this fixed point. If you start from the right-hand side, you converge to the other one. If you look at the sensitivity is infinitesimal, so it converges to 0 wherever you start, unless you start exactly on the separatrix. It tends to go to 0. But in terms of memory, if your memory is big enough, if you were trying to measure, encode a big delta x, and if they're different separatrix, if they start in a different Bayesian attraction, they'll converge to different fixed points. So you have a perfect 1-bit memory that'll last forever. So if you put something on the left, it'll be always on the left. If you put it on the right, it will be always on the right, meaning it has good discrete memory, but bad learning signal in this case. This can be generally quantified. This kind of phenomenon can be generally quantified using the Lyapunov exponents. Just to remind you what it is, it's a single number associated with a perturbation and how that evolves over time. So if you have an initial condition, you're perturbed by some vector, and you look at how the distance evolves over time, that in the limit, if this tends to diverge or converge, you have a Lyapunov exponents that are negative or positive. And for each initial condition and each perturbation, you'll have a Lyapunov exponent, but under general conditions, you can actually find that within a single Bayesian attraction, basically all states share the same set of Lyapunov exponents. So that's the same as the dimensionality of the system. So we can just talk about the set of Lyapunov exponents for that Bayesian attraction in most cases. And long story short, whenever you have a positive Lyapunov exponent, when you have like an unstable fixed point where you have trajectory that diverges from each other, the corresponding backpropagating gradient for recurrent neural network tends to explode. And whenever you have a stable fixed point like structure, you will have negative Lyapunov exponents, which corresponds to vanishing gradient. And then the special case where you have 0 or null Lyapunov exponent, you will have a marginally stable situation. So this is like a line attractor case where you have one dimension, that's the line attractor dimension, where the Lyapunov exponent is 0, and the normal direction, you have negative Lyapunov exponent. Any change you make, you push the state along the line, it just stays there forever. So that's what this marginally stable means. And in this case, the backpropagating gradient for learning signals will last forever. It will not decay, it will not explode. So the quest is, can we find system with as many Lyapunov exponents that are 0 as possible? And of course, continuous attractors, as I just showed you, is the primary candidate. Just to remind you, there's no flow on the low-dimensional manifold, this continuous attractor, and it's attractive to the case. And it's, we already talked about this, but during the delay period, basically in this memory task, you want to create a very, very flat, perfectly flat system, so you can store continuous values along this manifold. Of course, I will give you a cartoonish demonstration of how how balls will fall down if you change a little bit the energy landscape. This is known as the fine-tuning problem. If you change the system just a little bit such that the thing is no longer perfectly flat, you will no longer have a continuous attractor. So this fine-tuning problem is exactly that. So if you change the parameters of the system, it can easily destroy a continuous attractor. It almost always destroys a continuous attractor for most cases, if your perturbation is, general enough. And the problem is in biological systems, let's focus on biological system, there's always some fluctuations in the synaptic strengths. For example, there's synaptic turnover and drift. The learning signal, if there's learning going on, long-term plasticity rules will add noise to the system because there's stochasticity in the learning process itself. There's ion concentration changes, temperature changes, you might have had a beer. Many different things would change these parameters of the dynamical systems. So if there's a issue like this, like a fine-tuning problem, this is really bad. So here's an example of a system with a line attractor. This is a two-dimensional example where the dynamical system is x dot equals minus x plus rectification of a linear system. And you can produce a perfect line attractor by exactly choosing the W and B. But if you change any element in W or B, you would have typically these two types of bifurcation, meaning that line attractor, the exact line attractor of the black line where the flow was 0 goes away, even if your perturbation is infinitely small, and your states will either diverge to infinity or converge to 0 in asymptotic time. Here's a slightly interesting case where you have the bounded line attractor. This is inhibition-dominated line attractor. The weight matrix is down here. It's 0, 0 on the diagonal, -1, -1 on the off diagonal. And in this guy, when you perturb the weights, it could turn into this single fixed point in the middle where it converges to the center, or it could be this two stable fixed points at the edge converging to the two. This is slightly surprising to me because the linearization of the system would say the eigenvalues of the system would either become positive or negative if you perturb it. So I would have expected one to be a diverging system and one to be a converging system. But because of the limits of the bounded line attractor at the edge, it becomes actually both convergent systems. So both of these are vanishing gradient type systems at the end. Anyways, so these kind of fine-tuning problems is an issue in terms of using the continuous attractors as a theoretical tool for understanding neural dynamics, because it's very strange, right? Because if you think about the space of all possible neural dynamics as this box, each of these points in this box being a dynamical system, if you have fine-tuning problem, your continuous attractor solutions would be just isolated points in here, and any perturbation from it would destroy it. But because of these perturbations in the and the weights, natural perturbations in the weights, the neural system, the biological system, or the stochastic gradient descent learning recurrent neural network system will never be at just exactly one point. It'll just continuously move around. If there could be compensatory mechanisms, but it's not going to be maintaining this fine-tuning issue. So it's going to be never actually a continuous attractor, mathematical continuous attractor. But at the same time, the behavior of the animal, if they can perform working memory tasks pretty well, even if it's a continuous valued working memory, the analog working memory problems. So why does this, not degrade the working memory performance of the animal too much if this is a mathematical problem? Is it a apparent paradox? Question mark. So I'll first tell you, continuous attractors are not the only ones that has zero Lyapunov exponents. So the quest here is, if continuous attractors are these fragile objects, maybe we can find other systems that have analog working memory but are not continuous attractors. So there's a system that's well known to have a zero Lyapunov exponent, and that's a stable limit cycle dynamics. So a stable limit cycle is, as the name says, it's an oscillation system with a nonlinear oscillation system where it has a particular waveform and it oscillates around this limit cycle, and it's stable, meaning it's an attractive manifold. But it's not a continuous attractor because on the manifold of the limit cycle, the flow is not zero. But this system has a zero Lyapunov exponent because if you think about it, if you perturb the system at xt0 by some delta t, that difference will remain the same. The two trajectories after a full cycle will still have the same difference. The difference will not go away, unlike vanishing gradient or exploding gradient systems. So this means this phase difference in stable limit cycles are not forgotten. So this means we will have one zero Lyapunov exponent per stable limit cycle dynamics. And if you have, there are several ways of doing it, but if you have multiple stable limit cycles that are not interacting with each other and they have different periods, and the periods are not multiples of each other, rational multiples of each other, then we get a quasi-periodic tori attractor system. And one good thing about the stable limit cycle and quasi-periodic tori are that they are structurally stable, meaning most of the perturbations you make to the system, small perturbations, does not cause bifurcations. It'll be a slightly different stable limit cycle, but it will not just go away and become, 3 fixed points. Of course, it happens if you do precise manipulations to cause the bifurcation, but it's not the typical thing that happens for perturbations. So that means we have well, I didn't talk about chaotic system here, but we have a class, several classes of dynamical system with different properties. So you can have one fixed point, which is just fading memory. If you look at the population activity over time, it converges to a certain firing rate pattern. Neural activities for each neuron will converge to the same value for different initial conditions, and the backpropagating gradient, this learning signal, also converges to 0, so it has vanishing gradient. If you look at the Lyapunov spectrum of corresponding to that attractor state, you get all negative Lyapunov exponents, meaning it's all vanishing gradients. Not good for learning and not good for memory either. We have bistable system with two fixed points. It converts to 2 different values potentially, but the learning signal also vanishes. If you look at the gradient, the Lyapunov spectrum, it's all negative. If you have a line attractor, if it's a one-dimensional line attractor, it'll maintain, there's a persistent activity difference that's maintained over time, both forward in time and the gradients backward in time, the sensitivity backward in time. And the Lyapunov spectrum will have exactly one zero Lyapunov exponent. If you have a chaotic system, all is chaotic, and the learning signal tends to go to infinity. It diverges because you will have positive Lyapunov exponents, and these would cause exploding gradients. If you have stable limit cycles, then your population activity will be oscillating, and the learning signal backwards will be also periodic. And if it's a stable limit cycle, there will be one zero Lyapunov exponent and all negative otherwise. So that's the summary so far. The conjecture is that these are the only two possible ways that you can have robust, in the sense of not fine-tuned, dynamical system structure that does not suffer from the exploding and vanishing gradient problem. So that means stable limit cycles, or these quadriperiodic toroidal attractors, can be useful for both learning and memory. So let me demonstrate first how to profit from for learning. So what we're going to do is we're going to find some recurrent neural networks. We're going to try to use this, what we just learned, to train some recurrent neural networks. We'll initialize the recurrent neural networks in the regime where they will have no exploding or vanishing gradients over time, and train on difficult tasks. We're going to consider vanilla tanh RNNs and gated recurrent units RNNs, because for these guys, we know exactly the parameter regime for hop bifurcation. So we can create, we already know exactly how to generate these oscillations or these other oscillations. So if you have just two-dimensional system, two-dimensional recurrent neural network, what we can do is parameterize by a rotation matrix with some theta and some gain alpha. And in this theta alpha space, we know exactly when the largest Lyapunov exponent is 0, this white part, and the smaller Lyapunov exponent is also negative. And we also know what frequency of oscillations they will have. So what we can do is then sample from these parameter spaces, create a bunch of pairwise oscillatory systems. So generate, you have 100 neurons, 100-dimensional recurrent neural network. Every 2x2 block will be initialized as an oscillator with different frequency and different nonlinear stable limit cycles. But during the training, you're allowed to change all the entire matrix. So it's just an initialization scheme for the weight matrix. We're still optimizing the full matrix. We're not constrained to be of this parametric form. And you train this on difficult tasks. This is a copy memory task where you have given some symbols at the beginning, and 2,000 steps later, you have to recall these symbols in a certain way. So if you have vanishing gradients, you can't really solve this. This is a training graph for test loss, where the ones that has this small limit cycle symbol are using this particular proposed initialization scheme, and this one is like an orthogonal initialization, and we have LSTM, which has like a baked-in continuous attractor cell memory system. So all of these will compare. Only the ones that has this limit cycle initialization can solve this problem quickly enough. We can make it a random delayed version, this where the memory content at the beginning of the trial has to be read out at some random duration. In this case, only the GRU with the particular our initialization can solve this, and the final solution is not oscillating at all. So because of the random delay, if you have an oscillation, it doesn't help you. So this, what this initialization is doing is it's helping you to reach different solutions better. Right? It's not about can you express that solution or not, because they're all the same expressive power. It's how it's a trainability problem, right? Can you reach these solutions? I'll skip these for the interest of time, but basically what we showed was that this is this makes sense, and it works for learning problems. And the thing is, if you have these null Lyapunov exponents, and you have this, then you can implement an analog working memory system with it. If it's a case where the null Lyapunov exponent comes from a continuous attractor, you just need the continuous attractor and you're done. But when it's not a continuous attractor, like a limit cycle, you may need a reference, because there would be, you need to keep track of time. I'm going to show you an example system where we proposed a bump of activity on a ring without a continuous attractor. So this is a highly theoretical, simplified system where you have two oscillators with two neurons each. So the top two neurons have this delay due to axonal conduction. So they're oscillating at cycle tau, and the bottom two independent oscillator, same cycle tau, because the lengths of the axons are the same. They're same biophysical neurons, type of neurons. So this means if you look at the firing timing, these are spiking neurons, they will be firing at some period. These first pair and the second pair, the red ones, will be firing at different times. But the phase difference between the two oscillators is a free variable. You can set it to anything. They could be synchronous, or they could be, off, anti-phase locked, or any other phase, right? Because they're independent oscillators. So that's a candidate for circular memory, like a ring attractor. You can encode your information in that phase difference. But then how do you convert that phase difference into a spatial bump, right? This is where this delay line idea comes in. So you have, from the first oscillator, you get a spike that takes some time to go across the delay line, and a spike from the second oscillator that takes some time to go across the line. And depending on the phase difference between the two oscillators, they will coincide at different locations, spatial locations in this delay line. So if you have a bunch of coincidence detectors, let's say some nonlinear dendrites components, they will detect this, and you can have, you can wrap around the circle if you want, but basically what you will have is each neuron will have a tuning curve for different phase differences, and as a population, you will have a bump of activity because of the distribution of the synchrony detection that can move around as same. It will look the same as a bump attractor on a ring, but this is without the bump attractor. But of course, well, I told you that the stable limit cycles don't have this the fine-tuning problem because they are structurally stable, but this system does have a fine-tuning problem. Mainly because what the strong assumption here for this to work is that the two oscillators have to be exactly the same period. If the periods are slightly different, then you'll have a drift in terms of the phase difference, right? And that's you change any parameter in these neurons, it will change the period slightly, and they'll immediately destroy this. So this system will also have a fine-tuning problem as a working memory system. As a recurrent neural network, we don't have this problem because when you're doing artificial neural network training, you go back in time and you know exactly what time, what happened. So you don't need this copy. You just have that information when you're doing backprop. But here, because we have to implement this all in oscillators with a reference, you cannot do this. So the last part of this is asking, seems like, we have two different solutions. We try to come up with some way to get analog working memory and learning, but seems to both have this fine-tuning problem. And what we've seen in the literature is that, there's a lot of evidence for these approximate continuous attractors. They find it in fish, they find it in mice, they find it here and there. There are lots of evidence that these things exist and they are observed. So maybe it's not really a problem. So does it matter in practice to have this fine-tuning problem? So far the evidence, circumstantial evidence says it's probably not a problem. And a lot of people have said this, but we lack rigorous theory to precisely say this. So let me give you some theoretical background that supports this. So the observation is that if you take one of these theoretical continuous attractor models and you perturb it, I already showed you this one. On the right-hand side, we have a low-rank RNN that implements a ring attractor. If you perturb it, it either becomes a limit cycle or it becomes this, breaks down into these fixed points, stable and unstable fixed points on this ring. This also happens in other implementations of ring attractor. This is the Neumann system. It breaks down into many different fixed points. I will not go into the detail, but we have tried several of these theoretical or numerical ring attractor system, perturb the parameters. It all turns out that they still have some sort of ring, and it's some sort of they're kind of slow flow on the ring. And of course, in the case of the line attractor, it was a slow flow on that, wherever that line attractor was, with zero flow. After the perturbation, you still have slow flow. This color gradient here is the log speed of the dynamics. And this is supported by the so-called set of theorems that are called persistent manifold theorem. So if you have a continuous attractor manifold, this M0, where you have zero flow on the manifold and you have attractive flow towards the manifold, such that the attractive flow is uniformly away from zero. There's always some attractive flow everywhere. Then if you add some perturbation P, this perturbation has some uniform normal 1, for some small epsilon, this perturbed system F plus epsilon P bifurcates into a slow manifold, meaning it's still an attractive manifold. It's still an invariant manifold, meaning if you're on the manifold, if your initial condition is on the manifold, it will stay on the manifold, and it's going to be slow on the manifold relative to the other flows that are around it. So it's not exactly a continuous manifold, continuous attractor anymore. It is a continuous manifold, but not zero flow. So, and this makes sense, but let me demonstrate this graphically. So what I'm going to show you here is a ring attractor system. And what I'm going to do is perturb it with different kinds of perturbations. On the top, I have 3 random P with different flows, and I'm going to add this to the ring attractor, and the amount of perturbation is going to be this cyan line here over time. So here we go. So as you add more and more of this random perturbation, you will see that the ring manifold becomes a slow manifold. And the center one became like a limit cycle-ish thing, but it's broken here. And as you add more and more perturbation, it eventually breaks, as in it's no longer staying on a manifold, and it's no longer slow on the manifold. And this condition of normal, so-called normal hyperbolicity, is really protecting how much things are changing. And the benefit of having a continuous attractor manifold is that it does not break so easily. So in behavior relevant timescale, let's say seconds or minutes, maybe nothing will change because the flow is slow enough for you to function without a big error, right? So that's the idea. What about the converse? The converse, as in, if you train a recurrent neural network to do a certain task that requires working memory, will it also become a continuous attractor-like thing, right? So here, this is a training of a recurrent neural network, a vanilla recurrent neural network, to perform an angular velocity integration task. So it's trying to learn a ring attractor. This is the readout. It eventually learned it. And if you look at the learned solution on the right-hand side and analyze the flow, you can find, because we have a linear readout here, we can go and numerically find the manifold that is attractive that's read out to perform the task approximately well. And on the manifold, we will find a sequence of stable and unstable fixed points. And the flow on the manifold is slow. And in fact, if you look at these solutions, we have trained several of these networks and look at them. They have normal hyperbolicity. So what I'm showing you here is the eigenvalue spectrum linearizing the flow around this numerically found manifold, right? This slow manifold we found is parameterized by 0 to 2 pi on the x-axis. These are two different tasks. Both require a ring attractor to solve it, ring attractor-like memory to solve it. And on the ring, so at each point on the ring, there would be one eigenvalue, the largest eigenvalue that's close to 0. This would be the slow flow. And there will be a bunch of eigenvalues because this is a high-dimensional recurrent neural network. There are negative eigenvalues. These are the attractive dimensions. So you will be attracting to the manifold, and on the manifold it will be slow. And whenever this line crosses the 0 line, that's where the fixed points are, right? And what you can see is that there's a uniform separation between the slowest time scale on the ring attractor dimension versus the normal direction where the things are attracting for both of these tasks. And this was what we were typically finding for multiple of these systems. So I'm running low on time, so I'm going to just quickly conclude by summarizing these findings together. And what it says is that fine-tuning problem is not really a big problem. It's mathematically, we care about it because, in dynamical system theory, what we care about is the topological structure of these fixed points. If you have 3 fixed points versus 5 fixed points, that's a very different system. If you have a continuous attractor versus no continuous attractor, mathematically, it's completely different. So traditional dynamical systems people will consider this as a disaster. But as practically speaking, what we find is that these persistent manifold theorems guarantee that around these continuous attractor solutions, there's a region that is reasonably good approximate continuous attractors. So if you have biological noise, if you have learning noise, synaptic turnover noise, they will still be fine, right? And you can learn this too. So if you have a learning rule that's trying to learn to perform a continuous attractor like task, you will learn a approximate continuous attractor, and you will be guaranteed to be near one of these solutions as long as this normally hyperbolic condition will be met. Okay, so with that, I would like to thank my lab, especially Abel Shagudi and Piotr Soku. And most important funding sources for this work was the NSF Currier Award and the Champalimaud Foundation internal funding that allowed us to dabble into this crazy theoretical work. So thank you for this funding, and thank you all for paying attention.